Hi, I'm Deepak, and I'll be presenting our spotlight paper, Curvature Clues, Decoding Deep Learning Privacy with Input Loss Curvature. In this paper, we study deep learning privacy, which is of crucial importance in today's world. Recent research has highlighted the link between privacy, memorization, and input loss curvature. However, these studies primarily focus on input loss curvature in the context of training examples. Thus, there is limited understanding of how curvature behaves on test sets or unseen examples. Therefore, in this paper, we pose the following questions. What does curvature mean for test or unseen examples? What privacy properties can it capture? And what potential applications does it have? Let's look at what input loss curvature is. Input loss curvature refers to the curvature of the loss function with respect to input data. Formally, it's defined as the trace of the Hessian of the loss with respect to input. The figure on slide visualizes the properties of both low curvature inputs and high curvature images. Low curvature images are prototypical and well represented in the dataset. These are easy examples, whereas high curvature images are challenging, atypical, and hard, and are limited and have limited representation in the dataset. Our key insight for our paper was that we identified that test examples tend to have higher curvature than train examples. This is because train samples are optimized for and lie in flatter regions of the loss landscape. Building upon this observation, we developed a theoretical framework to study the train test distinguishability. Additionally, we proposed a new black box membership inference attack that estimates a curvature using a zero order method. This addresses limitations of prior curvature estimations that require access to model weights. We presented three theoretical results in our paper. First, we focused on the KL divergence between train and test examples under a differential privacy setting for confidence-based methods. Theorem 4.2 addresses the same for curvature-based methods, demonstrating that their performance is bounded by two parameters, the privacy parameter epsilon and the dataset size m. Finally, Theorem 4.3 establishes that beyond a certain dataset size, curvature-based methods outperform confidence-based methods. To apply theory to practice, we need to estimate curvature in a black box setting. However, prior works require access to model weights to estimate curvature. To address this, we propose a zero-order estimation method using a finite difference formula as shown on slide. We use the zero-order estimation to perform a membership inference attack, which tests if a given sample was used in training or not. The results of applying our method to such a membership inference attack are presented in Table 1 and Figure 2. Table 1 represents the AUROC and balanced accuracy results. Figure 2 shows the results of our method using a TPR versus FPR plot focusing on the low FPR regime. Clearly, the proposed technique demonstrates improved performance across these metrics. We also validated our theory by examining the performance of membership inference attacks against the privacy parameter epsilon and the dataset size m. These results align with the theoretical predictions. Figure 3 presents the results of privacy versus MIA performance, and Figure 4 illustrates the same for dataset size and privacy performance. We see that the proposed method curvature 0 LR exceeds that of other methods around the 30% subset size of the training set, and curvature 0 NLR, NLL performs prior methods above the 10% subset size. In conclusion, we investigated the role of input loss curvature in assessing train test distinguishability. Both theoretical and experimental results demonstrate that curvature based methods outperform probability and confidence based approaches for MIA. Additionally, we proposed a novel zero order estimation technique that enables black box MIA, achieving state of the art performance on CFAR and ImageNet datasets. Thank you. To know more about our paper, please scan the QR code on screen.